Morning, folks, and welcome to the end of our first full week. That's right, we did it! 1 week down. A lot to go. We are, in fact, almost done with our first very full week. We had just a couple more things that we got to get through today. We've got one more lecture, and of course, the first homework is due tonight. The homework is predominantly based off of stuff from last week. There may be a few electric field concepts built in there from early in this week, but hopefully it shouldn't be too much of a problem. Bit of a timeline. We are now on September 18th. 2 weeks from now, I believe, is going to be October 2nd. That is going to be our first exam. So we have a couple of weeks before that comes around. That will be cumulative for Unit 1, which includes the electric forces we talked about in Week 1. We have the electric fields we're talking about this week, electric flux that we're going to finish up talking about today and early next week, and then electric potential right at the end. Now, I did want to make a couple of things, announcements regarding the sort of communities here. I like to see the fact that you are all helping each other out in the various group chats that you have set up. Please, by all means, build a community, help each other, teach each other how to do these problems for the homework and the recitation. That's thumbs up. Those are positive learning goals. Like, that means at the very least somebody had to understand it well enough to explain it to somebody else, and I fully support that. Nothing wrong with that sort of thing. The one thing I do want to mention, however, is there was the first case of bad behavior was caught this week. Student in question perhaps did not realize this was bad behavior, so I'm making this exceptionally clear now. This is an online class. I'm probably what the internet would consider to be an elder millennial. I understand how easy it is to share answers, share feedback, Google around and find things. If I tried to track all of that down, I would die from exhaustion, and I'm already like 70% of the way there. I'm not silly. I know this happens, and we're trying to plan for it. So while I'm going to, again, encourage you not to participate in bad behavior, I know that there's very little I can do about your sort of personal messages and things like that. So we're just building assignments with that in mind. With that said, there is an expectation that you all maintain a certain amount of academic integrity while you're taking this class, and this means not cheating. Well, I want to make very clear one type of academic dishonesty that will not be tolerated in this class. Like I mentioned earlier, I support you folks talking to each other, not for exams, honor system here, but not my preference. But certainly for recitations and homeworks, yeah, get together, work together, teach each other, learn, great, thumbs up. The one thing I do not abide on any assignments in this course is outsourcing your efforts to somebody else. This means having somebody else finish an assignment for you by sharing your login information. And this importantly also means uploading your assignments to external websites that then provide you solutions. You know what I'm talking about if you know what I'm talking about. Those are absolutely unacceptable violations of academic integrity, and if caught, will meet with very bad repercussions. At no point during this entire course should you ever upload an assignment to an external website. I know the common refrain is that you want to check your results, and I understand. Checking your results is an important part of learning. But you can check your results either by using the built-in solutions that are released on Sapling at the end of the assignment after it's due, or you can come talk to me and I will give you solutions for days. I will happily tell you how to do every single problem in this class once they have been turned in. I've already caught one. And we are in what day? We are at lecture 5, and I've already found one. So I want you to know that I am looking. From here on out, if I find it for any of them, it is just straight up, very simply, you get a 0 on the assignment, possibly for the entire portion of your grade. So for example, definitely a 0 on the exam, probably a 0 for the entire Unit 1 portion of your exam grade. And I immediately refer you to academic integrity, and I recommend that they follow up with an official sanction. Like, this is the one thing I'm drawing the line on, folks, and I'm drawing it really firm. There will be no exceptions. I don't care how well-intentioned you were at the time. That one thing is the absolute inappropriate, not going to happen. So just please do try to keep that in mind. Other than that, if you want to talk to each other and learn, particularly on the recitations and homeworks, fully support that. In fact, if you do want to, say, make a Discord channel and you want to invite me, I'll help you with your homework problems in Discord. I don't care. Feel free. I fully encourage that. But please, no uploading your assignments to external websites to have other people do them for you. Alrighty, with that doom and gloom out of the way, let's get back to some good stuff. Physics! Wait, I said good stuff. Sorry, this is all I got for you. We're talking about more electric flux today, but because I skipped over these examples, I figured I'd take a time to do one of them out here up on the board. There's a question in the chat, what's the error tolerance on sapling? Usually defaults to 2%. Some problems are a little bit wibbly about that, so it can be as much as 5% and as low as 1%. If you feel there's a problem, that there's a sort of issue with the tolerance on the number that you submit, shoot me an email, I'll take a look, and I'll follow up with tech support if I need to. It has happened from time to time that they have them too aggressively set. It is relatively rare. I know it's a very common thing to be plugging in the wrong number, be convinced that you're right, and it's just like a numerical thing. Sometimes it is. Most of the time it's not, but if you suspect it, yeah, just shoot me an email and I'll take a look. Okay, what was I saying? Electric flux. I'm actually going to do a problem real quick just so you can get a feel for what we're actually doing. Now, I want to mention that in general, our definition of electric flux, which is a sort of measure of how much electric field is moving through an area. So for example, this right here indicates an electric field that is going through the area defined by my hand, versus this is electric field that is not. The way we define that is as an integral of the dot product between the vector E and a small little area dA. Now it's worth noting that often these integrals don't actually require you to evaluate the integral. In many cases where the situation is well behaved, meaning the area is constant, the electric field's constant, the angle between them are constant, those kind of things, this can actually be simplified to just a dot product between E and the total area vector of the thing. And we'll see that a lot in problems like this. Now, it's worth noting that the dot product between two vectors can be written out in two different ways. The way we mentioned last class was as the product of the magnitudes times the cosine of the angle between them. That is the sort of common way to do it in terms of magnitudes and angles. You can also write it out in terms of components. And this is more useful when you have your vectors in unit vector notation, like we do here. So we'll see that different versions of the dot product, or rather different ways of evaluating the dot product, may be useful in different problems. Here, we're going to find the component version to be more useful. In this next problem, it would actually also be, we'd actually end up using both. But I'm just going to do this one real quick so we get a feel for what's going on. The very first thing we're going to want to do is note that the electric field is given to us. So that is in unit vector notation, and that's usually a good hint that we should use the component version. But our area vectors are not. Now, the areas for each of these symbols themselves are actually pretty easy to calculate, right? They're just rectangles. So this is like a window and a trap door in a sort of room. Excuse me. There is 6 meters squared here, because that's just 2 times 3. And this one down here is just 3 times 4. It's 12 meters squared. Now, as a result, when we are doing our calculations, we're going to make use of this. But we also need the direction for the area vector. That direction is, in this case, upward for A2. And although it's a little bit hard to see, because this is trying to represent 3D on a page, this is pointing out towards you. So this is out of the page along this x-axis here. Now, we have that nice Cartesian coordinate system in the background, so we can see things that point out towards us are in the x direction. So the area vector is in the I hat direction. Whereas down here, the vector is up. If we look at our coordinate axis, we see that z is in the upward direction. So this vector is going to be in the k hat direction. This is useful because when we evaluate the flux over there, the flux for 1 is ex times ax plus ey times ay plus ez times az. That's this thing that we're doing. And if we just read off our vectors, that gives us ex 2 times ax 6 plus ey 7 times ay. Well, look, for a1, there is no y component to the area vector. So that's 0. And ez, which is -3, is also times 0. So when we do all that together, we get 12 newtons per coulomb meter squared, assuming I didn't make a dumb little arithmetic error anywhere. Okay, so the next step, let's come down here, and do the same thing for this vector down at the bottom. Now, we have going up, that's in our z direction, so we're going to go through the same process. Ex is still 2, but now ax is 0, ey is still 7, ay is still 0, and now it's ez, -3 times az, which, if you can read behind my giant head, is 12. So that gives us -36 newtons per coulomb meter squared. Okay, so I think there might be some issue with getting links in the chat. You might be able to leave it as a comment under the video. Alternatively, if you want to email it to me, I will post it as an announcement on the website. Folks in chat are discussing the Discord channel. I would suggest, as a general word of caution, to avoid putting your university emails in the chat, not because I don't trust your classmates, but because I don't know if you've noticed, but occasionally we get trolled with people, asking about how we can prove the moon exists, things like that. I don't trust YouTube trolls with your personal contact information. So just keep that in mind. I do try to remove the chat from the videos afterwards, but I'm sometimes slow in doing so. So just to protect your privacy, you may want to be careful about that. Okay, so with that said, I want to come back and finish up here and make an important note about these two fluxes. Note that one flux is positive, one flux is negative. You may be thinking, but wait, Professor Coyne, flux is a scalar value. Scalar doesn't have direction, so it shouldn't be important. But even though these things do not have a direction per se, they are not vector quantities, the overall sign of the result is very important. It basically tells you whether or not the electric field is in the same direction as the area vector when it's positive, as is the case here, or in the opposite direction of the area vector like it is negative here. With that said, positive and negative fluxes are going to become very important here, and we're eventually going to kind of interpret those as flux into something versus flux out of something. Imagine if you open a window, air can either flow in or out of your house, that kind of thing. So there's a comment in the chat that that there is some confusion over what EA cosine theta is doing here. That's because there are two ways of writing the dot product between two vectors, and the version that you use depends on the problem in question. In this particular case, we end up only using the component definition, and this is not used at all, simply because all of our vectors are in component format. What we'll find out is in this problem, when you go and do it, you can look through the lecture notes, you'll do the first part of this, probably using components, but then at the end, you'll have to find the angle between them. So what you would do in that case is you would set EX, AX plus EY, AY plus EZ, AZ equal to EA cosine theta. And then you would solve this result for theta. Now, the reason I mentioned it explicitly on this slide is because my typical observation is that when students write down the dot product, this is what they write down. In this problem, that won't get you very far because, well, I mean, you can still do it, but it's hard. It is harder because these angles are really difficult to define in three-dimensional space. And so here I mentioned this just as a convenience. How did I know, another question in the chat, how did I know to plug 0 in for all of these? I looked at these vectors. So I define these vectors in terms of the coordinate system. This one is in the x direction, this one is in the z direction. And anytime that's the case, there is an implicit assumption that the rest of the components, oops, sorry about that, that should all move together, are 0. So 12k is actually 0i plus 0j plus 12k. And then those implied zeros are the things that I plugged in here. All right. With that said, we have to move on from this practical example because we've got to talk about, come on, there we go. We got to talk about the most important application of flux from this class, and that is Gauss's law. Now, it turns out there are basically two types of surfaces, and I just held up 4, but there are two types of surfaces. There are surfaces that are open, meaning I can clearly define edges of that surface, versus surfaces that are closed. Imagine I rolled this up into a cylinder and then put caps on either end. Those closed surfaces have no well-defined edges to them. As a result, you could, for example, why am I doing this? Imagine you had a cylinder, like my Chewbacca coffee cup here. Note that a closed surface, like you could pour liquid into it, cap it, and that liquid would stay in there. That's what we mean by a closed surface versus an open surface like a sheet of paper. And it turns out you can define flux just as easily through a closed surface, indicated here by enclosing this central point charge in a sphere. That sphere has a surface area, and we define the flux through that surface area. This works just as well as the example we just did. And this is actually going to be an extremely important pillar of our understanding of electromagnetism. In this particular case, it turns out when you apply Gauss's law to this surface, you can actually derive the expression for the electric field. And we'll see that here shortly. But in order to do so, we have to define how the flux relates to the charge inside the surface. So here, as I zoom in, I have a sort of arbitrarily shaped green surface. Imagine this is like an amoeba. And this amoeba is just a three-dimensional blob. It's got little fiddly bits off the side. But importantly, inside that amoeba are two charges. A negative charge with magnitude negative q, and a positive charge, magnitude positive 2. So note that there is a net charge in here. Plus 2 is larger than plus 2q minus q gives me a net charge of 1. So I have charge in here. So I would expect that this arrangement to produce field lines like shown here. If I look at this and I just say, well, okay, how many of these field lines are going out of or into the surface? I look at them and, well, some of them do both. Like this field line comes out, goes back in, comes out, goes back in. So that probably doesn't contribute much. But some of these go off to infinity. And so we would expect there to be some type of flux here. We should be able to measure the electric flux through this surface. And it turns out the relationship between that flux and the amount of charge in here is very simple. I'm going to just box both of these equations because they are both important. They are actually just two versions of the same thing. It just kind of depends on how you refer to them notationally. But the basic idea is the amount of flux through a closed surface is proportional to how much charge is inside that surface. That's it. Simple as that. Total amount of flux is the amount of charge Q inside your closed surface divided by the permittivity constant epsilon naught. Its value is given here. Now, of course, we have a definition for how to calculate flux, and that's just what we've plugged in over here. It's the integral of E dot dA, and that is equal to Qn over epsilon naught. This thing in the middle is just what you get when you rewrite epsilon naught in terms of K. If you think back to Coulomb's law, remember that K is equal to 1 over 4 pi epsilon naught. So I can rearrange that and get 4 pi K is equal to 1 over epsilon naught. And so when I have 1 over epsilon naught, that is equivalent to 4 pi K. So those are just two ways of writing it that just depending on which physical constant you're comfortable working with. The important thing here, though, is this little thing right here. And I'm going to zoom in really, really close just so I can really super emphasize this. This is an integral. But for those of you playing the home game, you might note that there's something weird about this integral. There's a circle through it. That is not a mistake. That is a very important notational symbol. When you have an integral with a circle around it, this implies that you're doing what's called a closed integral, meaning as you do the integral, you end up back at the place you started. So this is how we define flux through a closed surface. You integrate over the whole thing until you come back to where you started. That total over the closed surface is what is equal to Qn over epsilon naught. And that's very important because open surfaces, like this sheet of paper, does not obey this relationship. Only closed surfaces with no holes and no gaps obey this equation here. This equation is called Gauss's law, and it is one of 5 equations in this course that form basically all of classical electromagnetism. We'll get into that in a little bit later when we get to Unit 3. But this is one of the pillars of this class. All right. Now, there are 2 ways to use Gauss's law. Either you can use information about the charge to tell you information about the flux, or you can use flux to tell you information about the charge. Different approaches have different applications, and we'll go through a few of those today. The first I will note is just this is an illustration of the same thing that was down here, just a little bigger. But I do want to note, and this is kind of important, the surface in question doesn't need to be physical. So for example, see if I can find a demonstration aid that will make me look sufficiently stupid. Yeah, sure, why not? Oh, no, definitely not. That has toxic resin in it. Sorry, you can imagine if I put a fishbowl over my head, that would be a real physical thing, right? It would be glass and it would be an actual physical surface around my head. But note that hopefully you're imagining that right now, even though I didn't put a fishbowl on my head. We can imagine a surface, a spherical surface around my head, something we're capable of doing. Gauss's law is totally applicable to that imaginary surface. And so that's what we do often in this class. We'll visualize imaginary surfaces. We have a special name for them. We call them Gaussian surfaces. And then we do our calculations based on that imaginary thing. Now, that's kind of what's being shown here. These 2 charges, they're not actually in an egg. We've just indicated that we're interested in calculating the flux through this imaginary Gaussian shape that looks vaguely like an egg. All right. Let me just double check what the sort of slides here are. Yeah, so there are 2 different applications of Gauss's law that we're going to go through today. The first is using the charge to figure out how much flux is through something. And then we're going to use the flux to derive things about the charges and about their fields. So in the slides here, from this point on, the next 1, 2, 3 slides are all examples of using these charges and relating them to the total flux. Then we do a couple of derivations involving Gauss's law, and that will be the end. I'm going to only spend a couple of minutes on this one, so I can spend a little bit more time on the derivation. So I won't get through all 3 of these examples, maybe 2. We'll see. But remember, for every slide that I show you, there is in the lecture notes up on Brightspace a version of that slide that has it explained, where Professor Mueller has typed up the explanation for this slide, and you can work through those yourself if there's something I don't get to in lecture. Okay, so here we are with a couple of Gaussian surfaces. Now these are imaginary. These SA and SB are meant to indicate that we are taking 2 charges and we're just imagining surfaces around them. SA encloses Q1, SB encloses Q1 and Q2. So we're going to apply Gauss's law here. Now we know in general the electric flux is the amount of charge, that total amount of charge inside a Gaussian surface divided by epsilon naught. Now this provides a very straightforward way of calculating what the charges are here. What we do is we take the flux information. We are told that the amount of flux through surface A, so that's the amount of flux through this one right here, is 5 coulombs per epsilon naught. Similarly, we are told that the total flux through here is 3. We can use that and just that, along with Gauss's law, to calculate what the charges of each one of these are. For example, for surface A, I know that the total flux is 5 coulombs per epsilon naught. And I know that is equal to the amount of charge inside that surface. Well, if I look over here at SA, look, and I see there's just 1 charge inside of it. And I often get questions about what do we mean inside. In this case, it's literal. I drew a circle, or I drew an ellipse. Is the charge inside that ellipse, like Q1, or is it outside of the ellipse, like Q2? So if we're talking about the red circle here, Q1 is the only thing inside, and so Qin is just whatever Q1 is. Note that the epsilon naughts cancel out, and I am left clearly with Q1 equals 5 coulombs. Simple as that. If I play a similar game for surface B, now I take the new total, 3 coulombs over epsilon naught, and I suppose I should actually be doing this in blue. I got that from right here. Now that's going to be equal to the amount of charge inside that blue ellipse. I look at it over there. Both charges are inside, so it's just Q1 plus Q2 over epsilon naught. Once again, in this particular case, the epsilon naughts cancel out. I'm going to drop out of the way here so I can then show you that 3 coulombs must be equal to Q1, which is 5 coulombs plus Q2. When I rearrange that equation, I get my result that Q2 must be equal to -2 coulombs. So we can use Gauss's law to take information about fluxes and use it to derive properties of charges. We'll be doing that throughout the later part of this unit. This is another example, a little bit more complicated, where now I still have the same 2 surfaces, but I have 3 different charges. I'm told what this one is, and I need to find what Q2 and Q3 is. Now, this is actually pretty simple when you work through it. Turns out surface A over here is 1, and we know what this is, so that allows us to find Q2 directly. Once we know Q2, we can land on Q3. I'd like to instead take the opportunity opportunity to do a slightly more difficult problem. And that is the one shown here. Now, we have 3 charges, just like the last example. There was a question about the previous thing here. Why did I do Q1 and Q2 on the top of this equation? Because remember, this is equal to the total amount of charge inside the surface. I'm talking about surface 2, and Q1 and Q2 are both inside the surface, so the total amount of charge inside is Q1 plus Q2. Hopefully that clarifies. Coming back here, I have 3 charges and 3 surfaces. I'm going to color code them just for the sake of completeness. I am told that the red is 1 coulomb over epsilon naught. That's going to be equal to Q1 plus Q2 over epsilon naught. Note that, as before, my epsilons cancel. And I get 1 equals Q1 plus Q2. If I do this surface here in blue, that is 2 coulombs over epsilon naught. Inside of there is Q2 and Q3. As is becoming a theme, the epsilons cancel. I'm left with 2 equals Q2 plus Q3. And then finally, my last surface here, I am told that that is 5 coulombs per epsilon naught, and that contains Q1 and Q3. Yada, yada, they cancel, and I'm left with 5 equals Q1 plus Q3. Well, wait a minute. I can't solve any of these equations. I don't know anything about them. Yeah, so that ultimately is the issue here. We don't have any of the charges, so we don't have any way of just solving one of these equations directly. Thankfully, we have 3 unknowns, Q1, Q2, and Q3, and we also have 3 equations. So we can solve these simultaneously. And there are a ton of different ways you can do this. It is a smorgasbord of options. You can set it up as a linear system, you can do matrices, you can do substitution, anything you like. Whatever works best for your brain. Probably the sort of simplest path forward is to just do substitution. This is, of course, also the most messy. So maybe, for example, I'll solve this equation for Q2, which tells me that 1 minus Q1 equals Q2. I can then plug that in here, which gives me 2 equals 1 minus Q1 plus Q3. Once I have that equation, I can solve that for Q3. I'll give myself a little bit more room to work here. To do 2 minus 1 plus Q1 equals Q3, or 1 plus Q1 equals Q3. And assuming I haven't made any bonehead math errors, which it's 9:30 in the morning, so that is not a guarantee, I can plug that in here. Q1 plus 1 plus Q1, and note that this is going to give me 4 equals 2Q1, which will in turn tell me that Q1 is equal to 2. Once I know Q1, that tells me Q3 is equal to 3. And let's make sure that that makes sense. 5, yep, that's good. And once I have that, I can also solve for Q1 here. 1 minus 2 gives me negative 1. I can't math. For Q2, let me just make sure that makes sense. Yep, and yes. So ultimately, I get that Q1 equals 2 coulombs, Q2 equals minus 1 coulombs, Q3 equals 3 coulombs. And if I add all of those up, I get that my total Q is equal to 4 coulombs. Substitution is usually pretty messy, as you can see here, but it is the one that I find students who are a little uncomfortable with this stuff is probably the easiest first step. Solving this as a linear system or using matrices or something like that, way sort of neater, but this is the thing that kind of fits with a lot of folks' brains, so that's why I did it. Good, and as you can see, this makes sense. Q1 plus Q3 does indeed add up to 5. Q2 and Q3 does in fact add up to 2, and Q1 and Q2 does in fact add up to 1, so we did our math right. Now this is only one of the ways we can use Gauss's law, where we take information about the flux and we use it to derive charges. We can also use charges to derive information about the flux, and that is actually going to be our way in to calculating the electric field. So there is a strategy that goes along to using Gauss's law to calculate the flux and therefore to calculate the electric field, and that is to take advantage of symmetry. Now, symmetry is colloquially understood as like things that you might see in the mirror, right? The human body is roughly symmetric across its center. I have an eye on each side, I have a nostril on each side, I have ears on each side, I have arms on each side, and while this is not, of course, universally true, you might notice that my face is a little bit lopsided. It's a good understanding of like typically what we think of when we think symmetric. But in physics, symmetry has a more specific and technical meaning. It means if you change a physical system somehow, but the physical laws that describe that system don't change, then that system is symmetric. So for example, here is a holographic disk, apparently, thanks to my green screen. So that's a bad example. I'll find something else around. Why was I so unprepared for my props? Let's see, is this any better? No. Yes, here we are. Okay, here is a disk. If I rotate this disk, the shape of the disk doesn't really change, right? It's still a circle, and the center is still at the same point. This is a system that is symmetric under rotations about this central axis. Note that if I rotate it this way instead, well, that changes it. Now it's looking different. So it is not symmetric under rotations this way. It's only symmetric around rotations around this central axis. This type of rotational symmetry, actually has a special name. We call it a cylindrical symmetry because you can take a cylinder, like the one shown here, rotate it around this axis, and nothing really changes. But if you were to rotate it this way or this way, that's going to change the process. You know, that is in contrast to, for example, a rectangular shape. Watch as my camera's white balance desperately tries to find a new normal, where I can do this and that changes. This is not symmetric this way. But if I were to, say, fold the rectangle, both sides of the fold do look the same. That would be a different type of symmetry. We're going to be interested in two main types of symmetry in this course because whenever you choose the correct symmetry for a problem, it simplifies the application of Gauss's law. The two symmetries we're really going to want to focus on is spherical symmetry. You know, if I take an actual perfect sphere, doesn't matter how I rotate it, it's always going to look like the same sphere. And then cylindrical symmetry. And so the way you know how to choose the correct symmetry for your Gaussian surface is you examine the symmetry that the underlying charge distribution has. If I have a sphere of charge, that charge is spherically symmetric, so I should choose a Gaussian shape that is also spherically symmetric, in this case, a sphere. Now, a rod, I can rotate a rod around this axis and it will look the same, but I can't rotate it this way. As we just discussed, that's a cylindrical symmetry, so a rod is cylindrically symmetric, so we choose a Gaussian surface that is a cylinder. Finally, if I had a little disk of charge, like my disk example here, that also has the same type of symmetry, so we would also use a cylinder for that one. And it turns out these give us a way forward to calculating the electric field for each of these. So right in the beginning, it was actually one of my office hours yesterday, I think, maybe the day before, I don't know, they all run together. A student asked me, where do these equations come from? There are so many equations on the slide, where do they come from? It's a valid question. Equations in this class are usually either a definition, something I just say, this is true, period, full stop. Take that for granted and then do something with it. Or they are derived, meaning I start from base principles and I build up to whatever that equation is. That's the example of all of the electric fields we skimmed over last class. Now, in this particular case, I gave you at the beginning of class a definition. E is equal to kq over r squared for a point charge. That's how you calculate the electric field. That was a definition. We did not derive it. But with Gauss's law, we can derive it. The way Gauss's law works in this case is first I examine my point charge. Well, my point charge is a point. You can think of it like an infinitely small sphere that has spherical symmetry. Therefore, I should choose a spherically symmetric Gaussian surface, a bigger sphere. And now I just want to write down Gauss's law. The integral, closed integral, over the surface of E dot dA is equal to k, sorry, that's not right, is equal to the amount of charge inside that sphere divided by epsilon naught. Well, in this particular case, the only charge inside there is q. So I'm just going to rewrite that as q. Well, this is a pretty simple equation, but we need to do a little bit of finagling to get it solved. Now, what I'm going to do is I'm going to take that other definition of a dot product. I'm going to take the dot product of E dot dA and rewrite it as the magnitude of E times the magnitude of dA times the cosine of the angle between them. That's just the definition of the dot product. That is equal to q over epsilon naught. Now, I know a few things about spherically symmetric scenarios. And that is to say, if I am at a fixed distance, then if this thing is really spherically symmetric, it means it doesn't matter how I rotate it. Then whatever the field value is here has to be the same everywhere along that surface. Otherwise, this wouldn't be spherically symmetric. As a result, I know that E is a constant, and I can pull it out of the integral. But we can go further. If we zoom in here and I look at the electric field coming out of this little area element that I'm integrating over, I need to draw the area vector. The area vector points normal to the surface. And if I have a sphere that is, imagine that this disk is a sphere in cross-section, the normal to the surface of that sphere always points straight out. Well, we know from spherical symmetry that the electric field does too. These two vectors, the angle between them is always going to be the same, no matter where we are here. If I have area and electric field, they're always going to be in the same direction. So that means I can also pull out the cosine from the integral. Moreover, the cosine is always going to be of the same angle, and I know what that angle is. When I have two vectors that point in the same direction, the angle between them is 0. So since theta is equal to 0, which implies that the cosine is of 0, cosine of 0 is 1, so that goes away, and I'm just left with E integral dA equals q over epsilon naught. Well, wait a minute. Integral of dA is easy. Integral of dx is x, integral of dy is y, integral of dA is just a. It's just whatever the area is. Well, what is the area for a sphere? It happens to be 4 pi r squared. So this is E times 4 pi r squared equals this. And note that when I solve all this together, I get that my electric field is 1 over 4 pi epsilon naught times q over r squared. This just so happens to be E equals kq over r squared, precisely the value that we knew already. So Gauss's law is actually where that equation comes from. We derive it. Gauss's law is a fundamental principle about electricity, about the electric field. And we derive all electric fields from it. So this one was straightforward. Oh boy, I can't imagine what it would look like if we went back and tried to do, all of these crazy, stupid things, like just remember how much effort it took to get the electric field for any one of these. Like, I barely touched this and it still took me 40 minutes. Well, turns out, with Gauss's law, those situations become extremely simple. Here is the rod with my cylindrical symmetry. This evaluates directly using the integral, and all of that whole complicated thing that we spent 40 minutes doing last class. It is all contained on this slide, and we get the same result in the end. What? Gauss's law simplifies these processes greatly for whenever you're talking about systems that have a nice, well-behaved symmetry. Now, there are a couple of tricks here. As far as the stuff that is going on in chat, I'll leave you to your Snapchats. There was a question about the Discord. I will post, I think that was sent to me. I'll post it on the Brightspace announcement. So if you want in on the Discord and you're not in my Brightspace class, shoot me an email and I can get it to you. So the one trick you have to be careful of when you're dealing with cylindrical symmetry is that although this is a closed surface, it is also discontinuous. Remember from calculus that smooth curves like this, those are continuous, but sharp corners are not. Those are discontinuities, and you can't integrate across discontinuities. So when you are evaluating your integral across this whole surface, you actually have to do it in 3 parts. You do the integral of the left side, the integral of the middle, and the integral of the end. The basic way that looks is you rewrite the integral of E dot dA as this is the closed integral over the whole surface, as the open integral over the left plus the same integral over the middle plus the same integral over the right. Now it turns out in this case here, the left side and the right side are not going to contribute. Because of cylindrical symmetry, the electric field is always going to point away from the rod. So the angle between the area vector and the electric field will be 90 here, 0 here, and 90 over here. So here theta is equal to 90. Here theta is equal to 0. Here theta is equal to 90. Now the cosine of 90 is 0, which means the dot product for the left-hand side and the right-hand side are going to be 0. You just have the integral over the mid. That evaluates to this result right here. You plug that into Gauss's law, set it equal to the amount of charge inside, and you end up with this result down at the end. Now, this is probably the important result for this page, and this is the one you'll most commonly be using. This is the electric field from an infinitely long, or at least a sufficiently long, charged wire. Now, we can do the same thing for a disk. The only difference is now we still use the cylindrical symmetry, so that same argument I just made still applies. The difference here is now we have a disk. This is going to be shooting an electric field out in opposite directions. So now it is the ends that have theta equals 0 degrees. and the mid that will have theta equal to 90. As a result, that changes what we have a little bit. Our integral becomes twice the flux through either end. You get one factor of EA from this side, you get the other factor of EA from this side, combine that together, and you get this important result for a sufficiently, why did that turn into an arrow? That was pretty clearly a rectangle. And this is the final result for a charged plane sheet. Interestingly, note that this is a constant. It depends on the surface charge density, sigma, but that's just a value. There's no dependence on R here, which means the electric field is the same strength no matter how far you are away from this thing. Okay, one last thing I will say is you can extend this result to a slab of material. That slab will now have some thickness, but the process is still the same. The same angles still apply, the same application of Gauss's law still apply. The only difference is that you now have three regions to consider. The region to the left of the slab, the region to the right of the slab, and then the region actually in the slab. Now, when you follow the same thing from the previous slide through, you get those results for these three different regions, and those are plotted here. Basically, on one side of the slab, you have a positive electric field. It then gradually decreases until it gets to the center, where it's 0. Then it becomes negative until it gets to the other edge, at which point it becomes constant again. Like I said, the lecture notes have a detailed derivation for both of these past two slides that I went through pretty quick. And here you go, we're done. Actually kind of on time today, finally getting my footing. This is the lecture quiz for the day. The basic setup is as follows. It's one of those, we give you information about the flux and you need to find out what the charge is. All we're telling you in this case is that the net flux here is 0, the net flux here is positive E, and the net flux here is also positive E. You need to, where E is the elementary charge, 1.6 times 10 to the minus 19 coulombs, you're going to have to infer which one of these charges, which one of these boxes contains which particle. Your options are proton, neutron, or electron, one in each box. Use Gauss's law to infer what's going on here. There's a question in the chat. Is the n hat the area vector dA? Specifically, this is the unit vector that points in the direction of A. Yes. So this n hat actually has a magnitude of 1. The way you would formally write that is that the dA vector is just dA in the n hat direction. So yeah, the n hat is used to signify the normal vector in this and most other cases. So like I said, this is the quiz for the day. It should be up on Sapling Learning. Don't forget, if you see that it's been completed, even though you haven't opened it yet, that's purely cosmetic. You should still be able to log in and complete the quiz. So other than that, I will touch base later today with a few more announcements, including the academic integrity policy. I'll send you all a link to the Discord that one of your peers has so joyfully set up for you so you can communicate and share stuff and that kind of thing. I'll take care of all of that after my next class. I have walk-in office hours today from 11 to 12. And that's actually one other thing I wanted to mention. My office hours policy are changing a little bit starting next Wednesday. Now that I've gotten a lot of the one-on-ones out of the way, 11 to 12 is becoming walk-in only. So you're still welcome to come by, but there are no appointments anymore. You can still go into Starfish and say, hey, I'm coming to walk in. Like if you want to let me know, totally fine. But no appointments during 11 to 12. If you already made an appointment, you still have it. That has not changed. In addition, I am no longer available for office hours on Thursdays starting next week. But otherwise, I remain available Monday, Tuesday, Wednesday, Friday afternoon from 1 to 5 for appointments through Starfish. I appreciate you folks using Starfish. I know it's another piece of tech, but there are about 500 students, and I am getting so many emails trying to schedule office hours. The only possible way I can juggle it is if we outsource it to a tool that automatically tells you when I'm booked up by somebody else. Maybe that'll change in the future, but for right now, I really need your cooperation on using Starfish. Other than that, folks, good luck on your quiz. I will jump out of the way and just leave it blank here for a moment if you want to pause so you can go think about that. Don't forget, Professor Mueller has question and answer sessions that I believe start right after this class. My office hours 11 to 12. I'm available very little bit this afternoon. I'm mostly booked through. But otherwise, folks, have a great weekend, and I will see you on the flip side.